Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can use the relationships between chords and a circle to calculate different parts of a circle. Sometimes that might be an arc length, that might be an arc measure. We might be able to see figure out what the diameter is. It all can base on some of the relationships that chords have with one another. So we're going to start by talking about this first theorem that says Congruent Corresponding Chords Theorem. What this is it says in the same circle or in two congruent circles, it doesn't matter, if two minor arcs are congruent, then their corresponding chords are congruent. And this is an if and only if statement, which means it goes both ways. There's no converse to it. So what that means is if this arc here, this minor arc, is congruent to this minor arc over here, then that means that this chord is congruent to this chord. Now note that those chords are not congruent to the arcs, but the arcs are congruent to each other, therefore the chords are congruent to each other. So how does that come into play here? Well, let's take a look at a couple of examples where we might use this. So in this problem, it says in the diagram, circle P is congruent to circle Q. We know that segment FG is congruent to segment JK, and FG and JK are both chords in our circle. We know that the measure of arc JK is 80 degrees. So what is the measure of FG? Well, using that congruent corresponding chords theorem, we can then say that if this is 80 and JK is congruent to FG and the two circles are congruent, that means that GF is also 80 degrees. Okay, that's the measure of FG or GF. Similarly, we can use something like this one, which kind of goes with that converse, that other idea, where it says if the measure of arc AB is 110, find BC. Okay, so if AB here is 110 degrees, because their chords are congruent, that means that their arcs, the minor arcs, are also going to be congruent, so the measure of BC is also going to be 110 degrees. Similarly, if AC here is 150 degrees, and we want to figure out what AB is, because we know that chord AB and chord BC are congruent to one another, that means that arc AB is going to be congruent to arc BC, meaning that they have that same measurement. So the measurement of arc AB is equal to the measurement of arc BC. So because we know that the total measurement around the whole circle is 360, we can take 360 and subtract out that arc AC at 150, which leaves us at 210 degrees. And then we know that those two arcs are congruent to each other or equal the same thing, so we can just divide it by 2 and get that the measure of arc AB equals 105 degrees. Okay, so that there is both options of, and just a few of the many ways that we can apply the congruent corresponding chords theorem, meaning that if two chords in the same circle or in congruent circles have the same length, then their minor arcs that go between those 2 points are also going to be congruent. Let's take a look at this next one here. So this next one is called the perpendicular chord bisector theorem. Now this one it has its theorem and it has its converse, meaning it goes one way and the other. So the perpendicular chord bisector theorem says if the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So what does that mean? So if this is our diameter and it is perpendicular to the chord, that means that these two segments of our chord are the same length, so it's bisected, and our arc is also going to be bisected. So that's really important to be aware of because it actually allows us to learn a lot more information about our circle just by knowing that that intersects at 90 degrees. The converse of it says that if we have a chord in a circle that's perpendicular to another chord, then that first chord is going to be the diameter. So let's take a look at how we can kind of apply this. So looking at this circle here, we want to figure out what HK is. Well, HK is going to be this whole circle here. So because we have our diameter JL and it's perpendicular to that chord HK, what that means is that we can actually use that idea to say if that this point right here, this NK is 7, it's going to be the same as this. And by that same theorem, we know that those arcs are going to be the same. So to figure out what HK is, the whole thing, we can just set 11x equal to 70 plus x, and we can solve for x and then add those two together. So 11x equals 70x. We can subtract x from both sides and get 10x is equal to 70, and divide by 10 to get that x equals 7. So if x equals 7, we get 77 for hj plus 77 for jk, which ends up giving us a total of 154 degrees. Okay, so hk is 154 degrees. Oh no, we were finding the measure of hk. Sorry, this whole step here is actually for our other problem. Oop, my bad. When we're talking about hk here, this is the segment, and the segment is referring to our chord in this problem. So as we mentioned before, because it's perpendicular, that means that our diameter bisects that chord. So if from n to k is 7, as we established previously, h to n is also 7, so hk is going to be 14. And then the measure of arc hk that's what's going to be the 154 degrees. So chord hk is 14. Arc HK is 154. Let's take a look at one other example in which we can use this. So we want to find the indicated length or arc measure in this case. So we want to figure out what the distance of CE is. So that's referring to our chord here. So because BD is the diameter, it goes through the middle of our circle and it goes from one side of the circle to the other. That's the diameter. And because the diameter is perpendicular to our chord CE, that means that from C to F, which is this point in the middle, and from F to E is going to be congruent by our perpendicular chord bisector theorem. So because those are congruent, if CF is 5, then FE is 5, meaning that CE is going to be 5 plus 5, or 10. To figure out the measure of arc CE, so now we're talking about our arc, we know that by that same theorem that this part of the arc is congruent to this part of the arc, so we can actually set those equal to each other. And we can do 9x is equal to 80 minus x, because we know arc CD, the measure of arc CD and the measure of arc DE are equal based on that theorem there. So we can just use this to solve for x and then use x to figure out what that arc, the measure of arc CE is. So we end up adding x to both sides and get 10x equals 80. We can divide both sides by 10 and we get x equals 8. So if x equals 8, then that means from the measure of CD is equal to 9 times 8, which is 72. And then the measure of DE is also equal to, I don't know why that was in parentheses there. Oh, the measure of DE is also going to be equal to 80 minus 8, which is 72. So then the measure of arc CE, which is the whole thing, we talked about in a previous video about the arc addition postulate that says I can add one to the other. So we've got 72 degrees plus 72 degrees, which ends up giving us 144 degrees for that arc as well. Okay, so that is how we can apply the perpendicular chord bisector theorem as well as its converse. Now we're going to talk about one last theorem here. This one is called the Equidistant Chords Theorem. It says in the same circle or in two congruent circles, two chords are congruent if and only if they're equidistant from the center. So to determine if a chord is equidistant from the center, what we have to do is we have to go from the center of the circle and draw a line that's perpendicular to our chord. And if that perpendicular line, because that's going to be our shortest distance, if those two lines are congruent, then that means that our two chords, so AB, is going to be congruent to our other chord, CD. But that's only if EG is congruent to EF. If our equidistances are not the same, if they're not both equidistant, if one is further away than the other at that perpendicular line, then they're not congruent. So let's take those into account and apply it in a couple problems here. So in the diagram below, we know that QR is the same as ST, and that equals 16. We also know that CU is 2x and CV is 5x minus 9. We want to figure out what the radius of this circle is. Okay, whoa, how awesome is that? We got to use all of this information that we have to figure that out. So what can we do to figure out what the radius of this circle is? Well, we have a couple of options here. For this first one, let's take a look at what the relationship is between these things. So we know that QR here is going to be 16. We know that ST here is also 16. So those are congruent, which means this is the same as that. So if those two pieces are congruent, then we know that we can solve for x that way. And then all we have to do is figure out what the radius of our circle is. So let's take into account those two pieces there and find that radius. So CU is going to be the same as CY, or as CV, based on that equidistant chords theorem. So what we can do with that information is we can solve for x. So 2x is equal to 5x minus 9. I can subtract 5x from both sides, and I can get negative 3x is equal to negative 9. Divide both sides by negative 3, and then end up getting x is equal to 3. Okay, now that we know that, what we want to do is use that information to figure out what our radius of our circle is. Okay, so what we're going to do now that we have what x equals, to find that radius, what we need to do is keep in mind that our radius is from the center of our circle to any point on the circle. So what I'm going to do is I'm actually going to connect from C out to Q. So now we've created this cute little right triangle here. We know what the distance of this piece, CU, is because if x is 3, 2 times 3 is going to be 6. So we know that this piece is 6. We also know that QR is a chord, but WX is our diameter. So in this problem, we can actually use our previous theorem that says if a perpendicular chord bisects, or if there's a chord that's perpendicular to the diameter, then that chord is bisected. So with that in mind here, that then means that QR, which is perpendicular to WX, and WX is actually one of our diameter, QR is bisected, meaning that this and this are the same. If the whole length is 16, that makes this side 8. So now we've created this right triangle here for us. Let me pull it out of our circle. Now we've created this right triangle here where the hypotenuse is our radius. The shorter leg is the equidistant center from our center of our circle to our chord, and the medium leg is going to be half of the length of our chord, that bisected piece with our diameter. So we just need to figure out what our radius is, and we can do that using the Pythagorean theorem. So 6 squared plus 8 squared equals r squared, and we end up getting 36 plus 64 equals r squared. Well, 36 plus 64 is 100. So 100 equals r squared, meaning our radius is going to be 10. Okay, so this was a little bit more of a complex problem, but what we did is we used that theorem that we talked about previously, that equidistant chords theorem, as well as our perpendicular chord bisector theorem to figure out what that radius is. Now let's take a look at one more question that's very similar, does the same sort of thing. So in this diagram, we know that JK is the same as LM, and they're both 24. Okay, so JK and LM are both of our chords here. And we know that they're both 24. So this is 24 and this is 24. Then we also know that NP right here is 3x, and we know that NQ is 7x minus 12. We want to figure out what the radius of circle N is. Okay, so what are we going to do to figure that out? Now that is the question. So up here at the top of our circle, I'm going to label this again. JK is 24. Because that radius is perpendicular to the line JK, or not the radius, the diameter of our circle, this SR here, because SR here is perpendicular to JK, that means it actually bisects it. So this side here is 12 and this side here is 12. So just like we did before in that previous problem, we're going to use this idea that bisecting to create a triangle right here. So we're going to create a triangle from the center of our circle to point P, which is 3x, which we need to solve for x. We're going to use this side JP, which is 12, and then we're going to create the radius from J to N. So let's pull that out, pull our little triangle out here. So we've got a 3x, we've got a 12, and we need to find our radius. Now we need to solve for x first. Now, based on that equidistant chords theorem, we know that because these two chords are the same in length, that means that the distance from the center point is also going to be the same. So we can do 3x is equal to 7x minus 12 and actually solve for x there. So I'm going to subtract 7x from both sides, and I get negative 4x is equal to negative 12. If I divide by negative 4 on both sides, I end up getting that x is equal to 3, just like in the previous problem. So this side here is not actually 3x, but it's in fact 9. So then what we need to do is figure out what r is, and just like in the previous problem, we can use the Pythagorean theorem to figure that out. And so we've got 9 squared, which is 81, plus 144 is equal to r squared. And if we do that math there, 81 plus 144 is going to be 225. So we get 225 is equal to r squared. And the square root of 225 just happens to be 15. So r is going to be 15. So if r is 15, that means that the radius of circle n is going to be 15 units. So again, the way that we use this is we took into account that equidistant chords theorem and solved for x, saying that I know this distance, I know that this distance here, let me draw it in black, this distance is the same as this distance. Then what we did is we also used our previous theorem, that perpendicular chord bisector theorem, to then say that I know that JP and PK are the same length because they are perpendicular to the diameter that goes across. Because we can find two of those sides, we actually can create that right triangle and use our right triangle math to solve for that. So that is a couple of chords that we can use in circles to find different things. We can find the radius, we can find the arc length, the arc measure, things like that. So if you have any questions, feel free to reach out, but that is how we can use chords in a circle.